Okay, hello. I'm here to talk about some recent developments at the Apache Point Lunar Laser Ranging Station, also known as Apollo, the Apache Point Observatory Lunar Laser Dash Ranging Operation. Full author list at the end, FYI. So very briefly, how this is going to flow. I'm going to say a little bit more about myself, talk about briefly why we do LR. Give a basic overview of the Apollo system, talk about the handoff to NASA in 2021, talk about why we installed an absolute calibration system in 2016, a basic overview of that system, some results, and a new systematic that was just recently discovered from those results. So who am I? I'm Nick Colmenares. I joined Apollo in 2014. I've never been to this conference before, so hi. Got my doctorate under Tom Murphy 2020, brief private sector stint. Was lucky enough to get in the NASA postdoc program with Steven in August 2021, and I came here to continue some research regarding the ACS system, help with the NASA transition, operations, etc. And also, these are my best buds. Okay, so very briefly, as Lillian indicated, LLR is basically like SLR, just longer distance. But why we do it, gravity and quantum mechanics are fundamentally at odds at predicting things at the smallest scales. Of the two, gravity is more suspect. It's been less thoroughly tested than quantum mechanics. For that purpose, the Earth-Moon system is a local, convenient, high-quality gravitational lab that we can use to test gravitational parameters, and additionally, it's sensitive to information about the Earth and Moon. So, basics of the system, it's at Apache Point Observatory in Sunspot, New Mexico, 3.5 meter aperture. The laser is a 2 watt average, 20 hertz, ND-YAG laser, frequency doubled to 532. The fundamental measurement that Apollo makes is a differential measurement, so there is a local corner cube attached to the secondary mirror that intercepts a small portion of the outgoing light, reflects it back. We time the receipt of those photons and time the receipt of the lunar photons against those. And the detector itself is a 4x4 array of avalanche photodiodes. The photosensitive elements are 30 microns in diameter, pitched at 100 microns. One side of the APD represents about 1.4 arc seconds on the sky and has about 100 picoseconds resolution. So the NASA transition, NASA took stewardship over Apollo at the start of 2021. There's been a lot of work regarding setting up best practices for operations logistics, which has been helped out a lot from folks from Peraton. We established a new data quality control check with the help of Vishnu Viswanathan to quickly identify centimeter level biases before releasing any data. We did release the first data release encompassing the entirety of 2021. This prior summer, we had an intern work on an automated scene estimation program, which is not Apollo specific. It can be used elsewhere, and it's to help the observer judge scene conditions and how she might need to adjust things to compensate for those. And finally, we're working on modernizing the control computer because it's really old 2001 Linux box, but still running. So the absolute calibration system, why did we do that? As you know, getting science out of LLR, we have to compare the data to solar system models and get out residuals. The spread of those residuals should be comparable to the measurement uncertainty. However, Apollo measurements traditionally have been at the 2 millimeter precision scale, but model residuals tend to be between 10 and 30 millimeters. So the question then was, is the difference between those two primarily due to data or model? And there was mixed evidence to address that, so we wanted to assess Apollo's accuracy independently, which is why we installed this absolute calibration system. So the overview of the ACS, what are we actually trying to do with the ACS? we're trying to send to the detector an optical ruler of truth pulses against which we can time range photons and calibrate them. And the way that we do that is with a laser, high rep rate, well-timed, short pulses, selectable pulses. This is a picture of the actual laser. The laser itself is a 1064 nanometer CSAM fiber cavity, frequency doubled to 532 as well. 80 megahertz rep rate, phase lock to a cesium standard. We have the ability to let individual pulses through to the detector at our request, and the pulses themselves are only about 10 picoseconds in width. So the calibration concept for this, let me first start by establishing that Apollo's clock is a 50 megahertz clock train, but as I just established with the ACS, that is an 80 megahertz pulse train. The way that we request, well, not request, but allow individual pulses through is to slice out a rising edge of a 50 megahertz clock signal, and then the next 80 megahertz pulse will be let through. So to that point, an 80 megahertz pulse train, those pulses should be are separated at 12.5 nanoseconds, but because of this selection process, at the detector, we'll actually see pulses separated at 2.5 nanoseconds, because there are 5 different possible positions relative to the nearest 50 megahertz sliced out signal. So this is actual data for a single normal point. Up here at the top, this is in red, these are the fiducial range returns. I don't think I said that before. The local corner cube, we call those returning photons fiducials or FIDs. So in red are FIDs, lunar photons are in blue here. The middle subplot here, this is ACS photons overlaid in cyan and magenta, and it looks really ratty because they're relative channel corrections that haven't been applied yet. But they have been applied in the bottom subplot here, which is why everything looks a lot tighter. And you can see that these peaks, these ACS peaks, are separated at 2.5 nanoseconds. And this is what we call a comb of teeth. And we can assert that these are pitched at 2.5 nanoseconds exactly, and interpolate between those and assign range photons timestamps based on their proximity to those ACS teeth. So how we estimate a timing correction, the particulars aren't super important, but all to say is that an individual photon timing correction is defined as the difference between the timestamp it receives from this ACS methodology and the timestamp it would have received in absence of this ACS methodology, which comes from an event timer self-test that's run once before and once after each data collection period. And then we want to come up with a representative value, a single value for each normal point to say what was essentially the average timing correction that had to be applied for this normal point. And then we make a histogram of that to study. And this is nearly 3 years worth of data of a ACS collection. And as you can see here, there's a magenta fit overlaid here, a Gaussian fit, that the centroid of which is nearly at 4 millimeters, which indicates that's Apollo's average range bias for this period. But once you remove that, the spread here is only about 1 millimeter. So the system accuracy in principle after ACS corrections are applied is at the 1 millimeter level and indicates that Apollo has never suffered large systematic errors. So furthermore, how can we take those results and extend them to normal points that did not have contemporaneous ACS photons in them? So didn't have ACS photons coming in at the same time as range photons. We actually discovered a new systematic. There's a strong correlation between ACS corrections here on the y-axis of this plot and on the x-axis here. This is how much this blue and red signal are separated by. So the more that our range signals are separated in event timer space, the more range error that we have. And we can use this linear correlation to estimate what a timing correction would have been for a normal point if it was receiving ACS photons at the same time as ranging. The fitted slope here, this is 0.6 millimeters one-way range per nanosecond of separation. So each additional nanosecond of separation between these blue and red signals gives you an additional 0.6 millimeters of range error, which translates to a 0.4% event timer range error for an imperfect overlap of these signals. So not only can we apply these estimated corrections to normal points that came after the installation of the ACS, but we believe this should be able to be applied for all historic Apollo runs because the same event timer has been used for the entirety of the duration of the experiment. And finally, down here, this is residuals. Residuals comparing these ACS corrections after subtracting out this model line. And the spread here is about 0.5 millimeter, whereas before, in absence of doing that, is 1 millimeter. So in the future, or going forward, we're going to update some data releases prior to 2022, come up with a 2022 data release, continue the control computer modernization, and once those things are finished, we're going to work on adding the ability for Apollo to target additional targets. So SLR targets like Lagios, as well as new next-gen lunar reflectors on the surface, as well as Lunar Pathfinder. And finally, these are some references. There is going to be a paper coming out very soon addressing what I just discussed, as well as a sister paper that addresses Apollo statistics and performance prior to the NASA handoff. And finally, here is the full author list, and that is it. Thank you.
Thanks for the talk. Any questions? We got one over there.
Hi, and thank you for the talk. It was really interesting. And maybe I don't really get it, but you showed that the wavelength of the laser is nearly infrared. But do you already measure with this? Because
it's an Nd:YAG laser that's frequency doubled to 532.
Okay, but the provided normal points are not with this wavelength measured, because as I know from the database that we have, only the green laser normal points are provided from Apollo.
Yeah. I mean, we don't range in infrared or anything. It's always in green.
Oh, yeah. Okay. Thank you.
Any other question? I was wondering, just to check, a little bit of confusion for me. So you see the residuals, or the precision of the data is 2 millimeters.
Right, just about, yeah.
Okay, but when you look at when you compare it to the model, you see an error up to 30 millimeters.
Yeah, the scale of the model residuals can be anywhere between, depending on what model you're using, it can be.
Okay, and that's the reason why you looked into this calibration.
Say again.
And that's the reason why you looked into this calibration.
Yeah, there was not clear evidence to say was it on the station side or more on the model side sort of thing. So.
Okay, so that was not clear at the beginning. Yeah, okay, I get it. And then you took a look at the event timer, or the thing that you corrected for sounds like it might be something with the event timer.
Yes, yeah. So this range error that I was talking about on, well, not the last slide, but the third to last slide. That applies to the event timer itself. It doesn't apply to the full 2.5 seconds of separation, or the full time that it takes for photons to go up to the moon and come back, just the 100 nanosecond gating of the event timer.
Okay, if you say that you always use the same event timer, the idea of also correcting old data sounds feasible. Van, you're an expert. What do you think? Sorry to call you out. Do you want to comment? I'm curious, because you know a lot. You want to comment about the barometer?
I don't know, unfortunately.
Okay.
What's your minimum elevation angle?
Say again.
What is your minimum elevation angle when you range to the moon?
That, I believe, is somewhere around 20 degrees.
Okay. Do you have a second barometer, or have you ever calibrated your barometer?
Apollo itself doesn't have its own barometer. We rely on Apache Point Observatory's barometer, and they may have a second one. I'd have to
Is
check
it a
into that.
Cetra?
Say again?
Is it a Cetra? Do you know?
I don't know offhand.
Because you would suffer from the same issues that the SLR network has with barometers, where there could be tropospheric biases at the few millimeter level, depending on how accurate your barometer is.
Right, right. Yeah, I can check into that, actually.
Yeah, that's a good hint. Thanks, Sven. Okay, thanks for the presentation.